This talk is going to be a little bit different. I'm going to talk in general about bioplastics. But before I get over that, I want to say it's great to be back on campus. I'm a Buckeye. I got my BS, MS, and PhD from Ohio State. And being beside the stadium brings back some really good memories. It's been a couple years since I made it back for a game. But I used to live in the stadium. Does anybody remember the Horseshoe Stadium Scholarship? Yeah, I used to live there. I used to live in Session. Did you live there?
I didn't live there, but I knew many who did, and it was always fun to go to sneak into the stadium through the dorm.
Yeah, we go through the dorms. We actually played football. One year we had a really bad blizzard, and I was an RA, and a lot of students couldn't get home, and we did an awesome job. We organized football competitions from different dorms, and they all showed up. You know, this dorm was playing that dorm at 2:15 in the morning, and at 3:45 the next dorm would show up, and we had a great time. We used to go up and study on top of the bell tower. And can you imagine that today, being up on top of that bell tower that has no handrail or anything where you could just plop off and fall, I don't know, what, 10 stories? That was way before Wi-Fi. And then you could feel the weights. The weight training team would be down and below the southwest tower. And when they dropped their weights, you could actually feel the stadium shake. I don't know what kind of weights these kids were lifting, but man, it was incredible. So it's good to be back. I'd like to talk a little bit about some of the work we're doing at Iowa State in terms of bioplastics, and I'll talk real briefly in general about what are bioplastics and what's going on in the industry right now. This is something that's really taking off, and I'll bring up some points of what's going on, and we'll talk a little bit about these protein-based plastics, and I think Dr. Schrader is going to talk quite a bit more detail about what are the advantages of these protein-based plastics and how they actually do some things that we didn't expect them to do. Then we'll get into some other applications, not so much to pots. Everybody's seen what's going on here and everybody knows why we're doing this, but I'll talk about some other stuff that we're doing at Iowa State in terms of that. I'm the chair of the BBRT, which is the Biopolymers Biocomposites Research Team at Iowa State. It was formed in 1995, and it's basically there to promote the use of bioplastics, to get industry to come out and take on and use bioplastics and encourage the use of them, the technology, and so on. It consists of 21 faculty. So it's a very broad group of people that are in the BBRT at Iowa State. People from myself, I'm in the Agricultural and Biosystems Engineering Department. We have people from material science. We have people from mechanical engineering. We have people from social economics that worry about things such as customers' willingness to pay. And so we heard some about that this morning, and we have people that look into that. Are customers willing to pay a little bit more for green? We have people from chemistry, chemical engineering, and so on. So there's a whole range of people, and we've never done a head count, but I'm sure there's well over 100 graduate students and postdocs that are involved with 21 faculty. Now, we do things like have workshops, we go to trade shows and so on, but the big thing that's going on right now, we're in phase one of putting together a National Science Foundation on bioplastics and biocomposites. We are in collaboration with UMass Lowell. Iowa State is the lead institution, and what we're doing is we're putting together the premier center on bioplastics and biocomposites. It's an industry university cooperative research center saying that NSF gives us some money, but we also have to get money from industry as well. And so what we're doing is that forces us to be very industry focused. Now, I came from industry. I worked at Emerson Electric for 12 years before I came to Iowa State. And so I know what industry is looking for, and I know how to work with them well. And right now we currently have 7 members, and we need just a few more to reach that critical mass. We will go to phase 2 and do our final submission to NSF on March 4th of this year. Plastics. You know, there's lots of images up here that don't look very positive about plastics, but we also have things up here that could be polymers. Now, if you were at the first workshop, you can't answer this because you know the answer, but I asked my graduate students, particularly master's students, and don't usually throw something a little bit more difficult to them on a PhD exam. Can someone tell me what the difference between a plastic and a polymer is? Okay, if you've been to the first workshop, you can go ahead and answer it then, if you remember what that is. There is a subtle difference between a plastic and a polymer. You know, a polymer is many repeating units all put together. And so a plastic is a polymer to some extent. But when I go through this and I talk about plastics are man-made polymers. And when we get into bioplastics, it's going to be a little bit of a gray area because, well, is PLA a plastic or a polymer? So we're going to use these terms a little bit interchangeably, but a plastic is one that this comes from petrochemical feedstock for the most part. And polymers are things like skin, you know, the cellulose, leather, things like proteins that are amino acids and so on. So there's things that are out there. And we see a lot of things that come back from us in terms of when we try to dig up this non-organic carbon. And that's kind of a funny term. I'm stealing it from Professor Narayan up at Michigan State. He's the one I've first heard use that term, and I liked it. Non-organic carbon. Can someone tell me what non-organic carbon is? Or what organic carbon is?
It's all organic.
It's all organic to some extent. One could argue that, but Narayan took his term, and what he's saying is organic carbon is one that's a little bit radioactive, right? He talks about this, you know, that if I were to hold up a Geiger counter to one of us, we're a little bit radioactive because that carbon has went around the Earth and has went up in the atmosphere, got radiated, and came back down as carbon-14. Now you'd need a pretty sensitive Geiger counter to pick that up, but if we look at polyethylene that came from natural gas, it's not going to have any carbon-14 in it, so it's non-organic carbon. So to Dr. Schrader's point, he's correct, but I liked it when Dr. Narayan used it, so I'm plagiarizing the way he said that. And we see that there's all kinds of adverse effects. You know, they got this crazy picture that people see about using fracking to get natural gas, and that's going to be used a lot to make polyethylene and polypropylene. And so when we start talking about trying to make pots out of biorenewable materials, the price of these materials is likely to go down as more of this natural gas comes online, because that's a great feedstock. We saw what's going on over the weekend in West Virginia. They got a little bit of a spill from the coal industry. And then there was this plant of a natural gas pipeline that exploded down in North Carolina over the weekend as well. So these things are continuously going on. So there are prices to be paid more than just out of your pocket when we start recovering these non-organic. Now, Dr. Schrader said that plastics is not our enemy. Now, if I wasn't on recording, I would disagree with him. But since I'm being recorded, I won't disagree with him. I'll just save that. But plastics really are great. And all you got to do is when you leave the grocery store and you pick up that bag and it's got 10 pounds of whatever you bought in it, and that stuff is microns thick, you know, 50 to 60 microns thick, and it doesn't rip, that tells you that stuff is really good stuff. And the petrochemical industries had a lot of time to be able to figure out how to make polyethylene, polypropylene, polycarbonate, and Kevlar, and all these materials that have just great mechanical thermal properties. So they are a great material. And a lot of times they can be recycled. You know, if you look at this bottle, this is made out of PET. So Coke bottles, Pepsi bottles, they're all made out of PET. And down below they have a number 1 on them. Not because PET was the first plastic ever discovered, but because it's the most recycled plastic. There's a good infrastructure of how we can take and we can recycle these and reuse them and turn them into things like carpet and so on for the automotive industry or for your home and so on. But obviously it's limited resources, foreign oil department, and then we got the environmental impacts. There's all kinds of things that are not so good about plastic. What we'd like to do is take some type of biomass that's renewable or something that's renewable and turn that into food and stuff. Fuel and stuff, sorry. And this is the model that most people think is going to be what's going to be successful, is a biorefinery. If we set up a plant to make just PLA, the economics of that are not very easy to swallow. If we make a plant that takes corn to ethanol, the economics are not very favorable. So the idea is to have a plant that's a biorefinery, biomass comes in, and there's a number of different products that come out of that. Maybe fuel, maybe plastics, maybe both of them, maybe chemistries, whatever it is. And that's the model that we want to try to follow. And when we look at bioplastics, there's actually a wide range of feedstocks that's currently being used to make them. You can have starch. So I'm sure, like if we go to our student union, they have the plastic utensils out there, and they are just basically made of cornstarch, and they've been formed into the forms of whatever they need to be, and you can use those. The disadvantage being they're relatively weak. Now, starch is a great material because it's already a polymer. It's already polymerized sugars. So when you eat pasta, that's really what you're eating is sugar that is polymerized. Plant oil. There's people that's been using plant oil, castor oil, to make plastics for many, many years. So that's relatively old. But people's like Sammy's group has been using oil to do other things with that as well. So there's new technologies coming out of that. Plant protein. I'm going to come back to that here in a minute. But proteins are polymerized amino acids. And so we're already working with a polymer right there. And then we can do things like fermentation, fermenting some type of sugar. Whether that sugar is coming from starch, like corn starch, or maybe sugar coming from sugarcane, which would be a lot more direct path. We can also have things that are composites, that are a mixture, a hybrid. You know, something that's recycled plastic and is filled with wood flour, or filled some type of natural fiber. And so, you know, I'm in the process of putting up a new deck, and I'm looking at using these type of products. They're more durable. And in fact, it's a good thing, because what we're doing is we're taking this biomass that may be burnt or thrown into landfill, and so we're sequestering that carbon. It's never going to be coming, or not for a long time, going to be coming out. There's a lot of questions about bioplastics. Can they be recycled? And for the most part, the answer is no. If we look at PLA, PHA, PHB, theoretically they can be recycled, but there's no infrastructure. You know, it took the US a long time to set up the infrastructure to collect these and recycle these. There's little stupid issues that we have to worry about. That little cap that's on top, that's typically made of polyethylene, which is not compatible with PET. So there's an infrastructure that's already in place to do that. And so if we start throwing in other materials such as PLA, PHA, or whatever it is that's commercially being made into the recycling bin, that doesn't work so well. But here in a minute you're going to see how we can actually fix some of these problems, and people like Coca-Cola is addressing these issues. We can burn them for energy, which is not a bad idea. You can do that with any plastic. If I take it out and I burn it, you know, in the case of PET, we've invested a lot of money and energy to get that bottle. If I burn it, and assuming I collect that energy, at least I've recovered that energy back out of it. So there's LCA models that say that that's not a bad model to follow. Ames, Iowa, we have a power plant downtown, this big ugly building, that burn our trash. And at times we get 100% of our energy from trash burning. I think it's about 20% of the time that we are able to claim that. Composting. One would always think that composting is a good thing, right? I take my pot and I put it in the ground, it disappears in a couple of weeks, months, year, maybe a year, whatever it is, and it's gone. And that may be somewhat good that it's gone, but we have to ask the question, what happened to that carbon? Right? When we made this pot, we took corn that took carbon dioxide out of the atmosphere, a greenhouse gas, and we've done a couple chemical pathways, and now we've got the carbon in here, and if I compost it, more than likely that composting process is going to release some of that carbon back into the atmosphere, either as carbon dioxide or worse yet, as methane. So if I don't capture that methane, I may actually have had a negative impact on the environment. So composting may not always be the best thing. And so I know that sometimes that's not well received comment, but we have to think about how we compost. Landfilling. We think landfilling is always a bad thing. You got these pictures with all these bottles, bazillion bottles in landfilling. But actually, that's not such a bad thing, because I've taken my inorganic carbon that I've gotten from natural gas or wherever it is, I've sequestered that back into the earth. It's going to be a long, long time before that PET or that polyethylene breaks down and comes back in the atmosphere. So I've basically sequestered that carbon. So we need to think about these type of things. And then, I don't know, I had a crazy postdoc by the name of Shunker that came up with this crazy idea, depolymerizing. You know, taking PLA and turning it back into lactic acid so I could repolymerize it. And there's advantages to that, for example, with direct food contact. So there's lots of things that we can do with bioplastics, but we have to be smart about it. And not one solution is going to be best for any one plastic. Each plastic is going to have its own solution, and each product is going to have its own solution.